2, 1.
All right, we're going to be 6-2, last lesson before fall break. One-to-one functions and their inverses. Okay, so one-to-one functions and their inverses. So we're going to have to decide if functions are one-to-one, and then if they are, then they have an inverse. If a function is not one-to-one, it doesn't have an inverse. Okay, you have to be one-to-one to be an inverse. So let's first define what a one-to-one function is. 1-to-1 functions map one x value to one. Dear. Oh, the internet went down. Awesome. All right, resuming our recording. All right, so we're mapping one x value to one y value. Okay, so kind of what does that mean? Well, to be a function, what cannot repeat to be a function? X values. Do not repeat. And then also y values. Do not repeat. So to be a one-to-one function means your x and y values, neither of those repeat. It's one x to one y, and that's the one-to-oneness of it. Okay. Now, so if you've got a set of ordered pairs, you're just going to inspect that and say, well, are any x's repeating? If that's not, if there are no x's repeating, check the y's. Are any of those repeating? If neither of them repeat, then you've got a one-to-one function as a set of ordered pairs. I don't think there's any need in us going through examples of looking at ordered pairs. Now, with graphs, what was the test that we used to determine if a graph was a function? The vertical line test, right? So with graphs, to check for one-to-oneness, you got to make sure it's a function first. And then we want to check it with what's called the horizontal line test. With the vertical and horizontal line test. Okay, and that can determine if something's one-to-one. Examples, draw a couple of quick graphs here. Call it example A. So here's our coordinate plane. And craziness happening. All right, so horizontal line test, touches it twice, it fails it. Okay, so we could, if we get an equation, what could we do to it to decide if it's one-to-one? Maybe it's a function f of x equals 3x squared minus 5x plus 7. What could we do to decide if that's one-to-one? I could grab it on the calculator and check it with the horizontal line test. That'd be a good way to check it. Absolutely. So, I don't even have to graph that really. It's quadratic, right? So it's going to make that parabola shape. So would it pass the horizontal line test? Not going to pass it. And then, maybe where it gets a little bit more complicated is where maybe we've got a cubic function, 2x to the third, 5x squared plus x plus 4. That's a little bit more complicated. There's a lot more that can happen with a cubic function than there can, with a, an even degrees are pretty easy to tell. odd degrees, you're going to have to really look at it. So let's graph that. Y equals 2x to the third plus 5x squared plus x plus 4. Hit graph. All right, would that pass a horizontal line? No. So that's not one-to-one. So that's really a good way of checking one-to-oneness is with the graph and the horizontal line test. So not, no on that. Okay. So checking one-to-oneness, can't repeat x's, can't repeat y's, got to pass the vertical line test, got to pass the horizontal line test to be a one-to-one function. If it is one-to-one, then we can do an inverse of that, okay? One-to-one functions have inverses. If it's not one-to-one, it doesn't have an inverse, okay? Not a function that is an inverse. You may be able to find an inverse, but it's not going to be a function. A one-to-one functions have functions that are inverses of them. Inverse functions. Does anybody remember talking about inverse functions before? They're easy. Swap, domain, and range. If I swap a domain and range, what am I really swapping? At x's and y's. That's really what I'm doing. Okay. So when we're looking at functions, and we need to decide, are they one-to-one? And then decide, okay, well, if they're one-to-one, what's the inverse of that? So here's a function that's a set of ordered pairs. -3, 6, -1, 7, 2, 13, 5, -8. Is that a one-to-one function? Yeah, so we got no repeated x values, no repeated y values out of that. So we can find the inverse of that. And the way you note inverse is it's kind of like a -1 exponent, but you read it f inverse of x is how you read that. So it's not a -1 exponent on everything. It's the inverse function, which swaps the domain and range. So it swaps the x and y values.
So they 6, -3.
Yeah, so that first order pair turns into 6, -3, 7, -1, 13, 2, -8, 5. It's the easiest thing in the world when you're just given ordered pairs to find the inverse. But it's got to be one-to-one before you can do that. So they're going to throw one in there every now and then that's not one-to-one, and you're just going to get in the habit of just swapping x and y, and you're going to go, wow, that's it. And then you end up with a not one-to-one function that you found an inverse of that doesn't exist as a function. All right. Next thing is, what if it's not a set of ordered pairs? Maybe it's an actual function equation that they give us. (6x minus 7). That's our function. Is that a one-to-one function? Yeah. Would it pass the horizontal line test? Yeah, absolutely. It's a line that goes up and to the right. We know that about that graph. If you're ever in doubt of that, graph it on the calculator. Check it. Okay. So the next thing we need to look at is, how do you find the inverse of that? Well, go ahead. No. What's y in this problem? That's the y-intercept. What's y? Like y. F of x. What do inverses do? Swap x and y. Now, get y by itself again. Last step, we divide everybody by 6. and then convert it back into the inverse notation. F inverse of x, 1/6 x plus 7/6. And there's the inverse of that. Is that a function? Yeah, it's a line that goes up and to the right. Not nearly as steep as the 6x minus 7 does, but it's still a function. And that's the idea of one-to-one functions, is the original function is a function, and the inverse is also a function. That's what makes them one-to-one. All right. So swap x and y, solve for y again. That's going to get you your inverse function. That's really what you do. Okay. Let's look at one that's a little bit more difficult. Here's our function. Okay. What do we know about that function? Is there a restriction on the domain of that function? Yeah, it's x can't be 1, right? We know that about it. Is that a one-to-one function? Graph it and decide. Two x plus 1 on top. X minus 1. Keep in mind what's going through right here. It's a rational function, so we got to remember the stuff about those graphs. Right, what's happening at y equals 2? It's a horizontal asymptote. Okay, so these are never going to get to the same spot. There's always that little bitty gap in between them. Okay, so would this pass the horizontal line test? Yes, so it is a one-to-one function. It's a little weird looking, but it's a one-to-one function. Okay, so that means we can find the inverse of that. It's a little bit more difficult. You got several places where there are x's. And remember that inverse functions swap x and y. So everywhere there's an x, you put a y, and everywhere there was a y, you put an x. Well, that makes it a little difficult. We got to get y by itself, but it's in two places. So what do I need to do? I can't. They're already combined by division, so I kind of want to undo that. So how would I move this? Yeah, if I multiply both sides by y minus 1, that'll get that out of the denominator. And that'd be xy minus x. On the other side, we got 2y plus 1. Now, what are we trying to get by itself again? The y. So we need to get everything that's a y on the same side, and everything that's not a y together. So decide which way you want to go. I'm going to move this x back over here and move the 2y over here. Okay. So that'll give me xy minus 2y, and then x plus 1. Because if I subtract 2y from both sides, and then add x to both sides, I'll do 2 steps at once there. Just to get the y stuff. Anything that's got a y is on one side. Anything that's got an x only and no y's is on that side. Now, here's where we got to think a little algebra 1. What do I do here to get the y out of that? It's like just like it's been distributed, right? So it's like factor out the common factor, which is y. That'd be y parentheses x minus 2. Right? GCF of those two is y, so pull it out. Is that making some sense? Now, I can get y by itself by doing what? Dividing by the stuff in parentheses. divide by x minus 2. X plus 1, or x minus 2. And it's converted over to inverse notation, f inverse of x, x plus 1, x minus 2. What's our restriction? Yeah, x can't be 2 on the inverse. There. Now, to kind of tie that together with why is that 2 different than the 1 from the original function? What's the y value, at 1 there, or at what's the y value, the horizontal asymptote, where's it at for this original function? At y equals 2, ratio of the leading coefficients. Okay, so it's a horizontal asymptote. That's the y value. What does the inverse do? Swaps x and y. So if y is not 2, there's a horizontal asymptote at 2. On the inverse, the x not equal to 2 is coming from that. Is where that's coming from. So that's kind of trying to tie some things we've done in the past with what we're doing now that are still related. May not be quite as straightforward, but it's still related. Okay. All right, let's get one more example of finding the inverse. So let's say we had g of x is equal to x squared. And they tell us that x is greater than or equal to 0. So they're telling us a restriction to the domain, not saying discover it. They're telling you it on this one for a particular reason, so that when we look at our inverse, that it's one to, it's a 1-to-1 function out of that. Because what do we know about x squared? Is it 1-to-1? Not normally. But if you limit the domain to x's are greater than or equal to 0, you're getting that parabola shape, but you're cutting off the left-hand side of it. So you get this one side thing, which does pass the vertical line test and the horizontal line test. So that's what they're telling us that for, so that it makes this a 1-to-1 function. All right, we made that a 1-to-1 function by saying that. This is example G. Is that right? So let's find the inverse of that because we know it's a 1-to-1 function. That'd be x equals y squared. And how do we get y by itself? Square root. Now, which one of those do we keep? Well, y is by itself, but we got plus or minus the square root of x. Because anytime we take a square root in a problem to solve it, plus or minus comes in with it. Which side of that do we keep? Why the positive side? Yeah, because the x is greater than or equal to 0. The only y values that we had for that were that y's were greater than or equal to 0 as well. So the inverse, g inverse of x, is the positive square root of x. X is greater than or equal to 0 as well. This x is greater than or equal to 0 is the same as the range for the original function, because they've swapped domain and range out of that. So you got to keep that in mind, that the domain of your inverse is the range from the original. That's important. Okay, so maybe you want to note that somewhere. All right, last thing in this section is verifying inverses. Okay. Two different ways you can do it. One way is algebraically, and we'll cover that first. Algebraically involves the function composition that we did in section 1. Okay, so that's why we even did that. Okay, function composition: f composed with its inverse of x equals x, and f inverse composed with the original function in that order equals x. That's algebraic verification. We're going to do that. We're going to be asked to do that on a quiz. Algebraic verification. Okay, so let's look at an example of that. So R, f of x, and g of x inverses. Verify. F of x, let's just use 2x plus 3, and g of x, do 1/2 parentheses x minus 3. Okay. So to verify that they're inverses, we need to show both of these directions of composition. That verifies inverse. If one of those doesn't give me plain x at the end, they're not inverses of one another. Okay, so if one of those directions fails, they're not inverses. Okay, usually, unless we make a mistake, if one direction doesn't fail, the other direction shouldn't fail either. But you got to check, you got to show both of them to verify it. It's one of those, like in geometry, you know, you guys had to do those proof things. This is one of those proof things. You're proving to me that those are inverses of each other by doing this. So let's do f composed with g of x. So that means we're taking g of x and plugging it in to f of x. And working that out. So it's going to be x minus 3 plus 3. Because if I multiply 2 times this half, 1, right? And then 1 distributed across. So then what do we get here? Negative 3 plus 3. That equals x. I verified it in that direction. That got me what I need to say that they're inverses of one another. Let's do it in the other direction. G composed with f of x. 1/2 parentheses, and then you got 2x plus 3 minus 3. So that's going to be 1/2 times 2x, which is x. F of x and g of x are inverse functions. You verified that by doing those compositions. Usually it will fall apart the first direction. It will fall apart the first direction because it won't work. It doesn't work in one direction and not the other. Promise you that. But you've got to show me both directions to verify. That's that proof idea out of that. Okay, so that's algebraic verification, function composition. Another way of verifying that's a little bit more difficult to see sometimes. If you got good spatial sense, it's easy to see. And if the graph isn't too big, it's easy to see. Is graphical verification. Reflection across y equals x. Okay, so let's look at those same two functions that we had in example H. And let's look at their verification graphically. Okay. Graphically, I'm going to graph each of those on the coordinate plane. I'm going to use my calculator to do it, okay? So I'm going to y equals, it's the same two functions that we used on example H, okay? It's the 2x plus 3. I'm going to graph that as y1. y2, I'm going to graph as 1/2. And then x minus 3 in parentheses. We'll make sure you type them in correctly. And I'm going to go ahead and in y3, I'm going to graph the y equals x line so that I can see the reflection across it. We already know that these two are inverses of one another, so they should reflect across the y equals x line. I want to show you what that looks like. Okay, so we're going to graph that. So here's the 2x plus 3. The red one is the 1/2 x minus 3. And then the black line is your y equals x line. Notice that it's a reflection. This blue part reflects across, and it's down here, it matches up. They also cross on the y equals x line. That's important, okay? But they cross there. Now, are they always going to cross on it? If they're linear, they will. If they're, some other type of picture, maybe not, depending on what the actual function is out of that. But that's a graphical verification of that, okay? Graphical verification it's a little tough sometimes because it's hard to see. The algebraic verification, very easy to see. If it equals x, then it worked. If it doesn't equal x, it didn't work. The graphical verification is kind of tough, but it is a method for doing that. I'm going to ask you to do the algebraic one on the quiz. I don't show me the graphical verification of that because
quiz and a test is fine.
I'm hoping to quiz. No, we're not doing the test. Well, the test we'll pick up Monday after fall break with the rest of chapter 6 starting that Monday. I would love for us to just take our quiz tomorrow at the end of class, because this stuff you're going to see once you get started working on this, it's not that bad and it's pretty easy to do. So I would love for us to take our quiz tomorrow. That way, if somebody's starting their fall break early, that's fine. And then you're not crunched for time Friday morning, seniors, because you guys have a meeting at 8:30 Friday morning. They sent us an email last week saying that you'll have a meeting this Friday at 8:30. So that's one of those things that I want to try to avoid. All right, so on page 415, sorry.
May I have your attention,
11 through
please?
95.
Ms. Gladys, the blue shot sign-up sheet is in the office. Teachers, if you're interested in getting your blue shot at school, please.
Not very
sign up
often that I say, hey, guys, look at this at home tonight. But you might want to go ahead and get started on a few of them this evening or sometime today. And then that way tomorrow when you come in, you can have some questions to ask if you run into something that you have trouble with.
Your books are on sale during lunches. They're $75, but you can